Okay, so off we go. So last time we finished section 1.2, moving on now to section 1.3. So dot product, I believe you all have seen dot products before. So I am going to go pretty quickly through this. Again, tough choices. I can't do all of everything that's in the book. No time, right? So this section is going to be a pretty quick one. So y'all know the formula for dot product. There it is. Make sure you know it, of course. Easy one to know, though. That's nice. Make sure that you look through the section. Reminder, you're always responsible for what's in the book, other than what's in the excluded column on the content syllabus. And while we're here, quick comment, don't forget that there's this idea from linear algebra called inner products, and the dot product is the model. That's where inner products come from. And of course, inner products are very useful in lots of applications. So it's another little win for dot products. So now I have one personal little pet peeve. I'm going to call it a kind of a complaint of sorts about an idea related to dot products, and that is these words perpendicular and orthogonal. In a lot of contexts, including our book, these terms are used kind of interchangeably, and I think that's a mistake. But I think it's a missed opportunity. Let's say it that way. So the point is, there are two distinct ideas that are closely related to what we think of when we hear these words. Right? There's what I'm going to call the geometric idea applied to non-zero vectors. If you think about it, if you have two non-zero vectors, then you can talk about the angle between those directions that those two non-zero vectors point. So angle and direction are intrinsically geometric concepts. Right? And so, of course, y'all know what a right angle is. Okay, now, here is a closely related and yet importantly distinct concept, and that is what I'm going to call an algebraic idea, namely when the dot product is equal to 0. Now, the dot product is an algebraically defined thing. I'm sorry about this bright spot here again. Dot product is an intrinsically algebraic thing. When it's equal to 0 is of algebraic. Oh, I can put my head right here. It's of algebraic interest, you might say. Yeah. Okay. So, well, they're practically the same thing, right? But they're not identical. Not every instance of one is also an instance of the other. And if you're going to talk about a distinction between ideas, sure is handy to be able to literally distinguish the ideas and how you call them. So to me, if you have two words and two distinct ideas, you should use one strictly for the one and the other strictly for the other. That's just where I'm coming from, right? I mean, it seems like a reasonable strategy to me. So to me, perpendicular should be used only to refer to the geometric phenomenon that we're talking about here, about right angles, right? Which, very importantly, only makes sense if the vectors are non-zero. You can't talk about whether the zero vector is perpendicular to some other that doesn't even point in a direction. I guess you could say it points in all directions equally vacuously. It doesn't make any sense, right? And then there's the word orthogonal, which I think should be reserved for this algebraic idea. Right? So you can have vectors be orthogonal, but not perpendicular. So anyway, FYI, something to think about. Okay, so let's see here. Moving along, here is a quick fact that I hope you saw in linear algebra. If not, it's quick, it's easy, and that is that if you have a non-zero vector, and if you want to find the unique unit vector that points in the same direction, there it is. You just take your non-zero vector, divide it by its own magnitude. Boom, there's your unit vector. Okay, so again, hopefully familiar. Who cares? Well, it turns out that unit vectors are really very natural in some important ways. We're going to see a couple of those today. All right, so handy little trick. Okay, next quick idea I want to talk about, the idea of a component. Now, I suspect you might not have seen this in a linear algebra class. Maybe you did, I don't know, but you might not have. So the idea of a component is that if you have a vector W, that W has a magnitude, it's pointing a certain amount in a certain direction, but the thing is, it is also pointing in some sense, to some extent, in this direction. The direction indicated by some vector V. Like so. I mean, it's not 100% in that direction, but nevertheless, if the purple direction is the direction you care about, W is to some extent pointing that way, at least a certain amount. And so this is what we call a component. The component is that right there, and I emphasize this is not a distance, right? It is a scalar. It can be negative. If W were kind of pointing somewhat backwards of the purple direction, then that component would be negative. So an easy metaphor for any sports fans out there is think of the purple direction as that is the downfield direction, and think of the W vector as the displacement from where the ball was to where the ball became in a given play. The component says how many yards did you gain or possibly lose. Right? So natural, simple, easily relatable example of where that comes up in an unsophisticated context. Okay, so how do we compute it? Well, there's an easy formula. You'll notice that we can form this right triangle for which we can write down some trig. Notice that the component is involved in that trig, and then of course you can do a little bit of algebra. There's nothing to it, just like so, and specifically you can then solve for the component. And so this is a nice handy formula to make sure that you know. I of course also advise that you make sure that you know where it came from. Namely, I make sure you understand where that how that trig works, how this algebra works. By the way, there is one little slick move here, and that is in this step right here, we both multiply and divide by the same thing, namely the magnitude of V. It's a slick move, seemingly pointless, perfectly legal, but seemingly pointless. Nice because it allows us to reinterpret that numerator as a dot product and thus make all the trig go away, which is a good thing. All right. Okay, now, make sure you know that formula. Here is another take, though, on that same formula, and that is, notice that right here we have V divided by the magnitude of V. That, of course, is the unit vector pointing in the same direction. And if you rewrite this formula with that in that place, then you get this really handy, I'm going to say alternative formula, but really better, really handy interpretation of dot products, frankly. And that is that components are dot products with unit vectors. I think that's a really nice way to think about dot product. Dot products with unit vectors give you components. It's almost like you're saying dot products are components. Not quite, right? I mean, it very critically, the vector defining the direction does have to be a unit vector, right? But that said, still pretty close connection between something algebraic, the dot product, and something that we have geometric intuition for, namely components. So valuable little result there. Okay, pausing. Questions? How we doing? Everybody happy? Okay, projection. What is a projection? But this is another sad case, frankly, of terms being used kind of differently in different contexts, and it is what it is. Sometimes people will talk about what I have previously defined as component as being the projection. So just be on the lookout for, in different contexts outside of this course, the terms might be used a little bit differently in different contexts, whatever. In this course, we're going to use the term projection to refer not to the scalar indicating how much W points in a given direction, but to the vector that indicates literally the part of W that points in that direction. So again, big difference, right? Component's a scalar. Projection is a vector. Now, how are we going to compute that vector? Well, again, there's really not that much to it. It's an easy observation to make. Really, this observation comes from understanding what a vector is in the first place. It's a direction and a magnitude. And we already have a handy formula for how to compute the direction, namely the unit vector that points in the given direction. Old news. Right? And we also already have a formula for, it's going to be tempting to call it a magnitude. Again, you can't say magnitude or distance or length because this could be negative. W could be pointing the other way, right? So, but the scalar indicating what you want to multiply by that unit vector is the component. And again, we have a handy formula for that. So if you want to understand this vector, well, direction and magnitude previously noted. Right? And so here's our handy, convenient formula. Let's see here, I'll use the dark. This projection vector here, computed by that formula right there. Everybody with me? All right. Okay. All right, now, this is my favorite point of view on projections. There is another formula I'm going to show you momentarily, but let me point out why I like this. I like this formula because I'm no good at memorizing formulas. I can't. I don't know phone numbers, right? I don't know my driver's license number. But this is an idea. And I am pretty good at understanding ideas and remembering ideas. It's like I remember why a joke is funny. I don't remember all the words to it, but I remember why it was funny, right? And I remember the basic concept here that you can view a projection as being a unit vector direction times an appropriate scalar component. That makes sense. That's geometrically memorable, right? And that's really all this formula is right here. I also like the fact that this is what I'm going to call natural, right? This writes the formula in terms of fundamentally natural geometric objects. Now, your alternative is to take this formula and plug in the existing previously established formula for the unit vector and then kind of multiply it out, collect terms, etc. And now here's your alternative. This is the one that the book uses. Alternative formula for projection. Now, if what you're interested in is plugging and chugging, right? If you're interested in arithmetic, this is arguably better because everything it's right there. You take the W, you take the V, you put there, and then you start to plug and chug, right? So computationally, yeah, this has an advantage. Again, that's not what we're here for, right? So I generally tend to kind of discourage this formula. I think what we had up here, well, in fact, what I still have right here, I think is ultimately more natural and simpler, easier to remember, better connected to ideas, which, of course, is what this course is about. I think this is a better formula. Everybody see my beef here? Okay. All right. Okay. You're perfectly welcome, of course, to use this other formula. I don't advise it. Okay, real quick. Now, again, tough choices. There are a few examples in the book of how you can use vector algebra to actually prove theorems of geometry, and this is pretty cool. It is a very useful tool. There are stuff that you can do with vectors that in a high school algebra class, a high school geometry class just wouldn't have worked. Right? So check them out. I think there's at least one on the homework, by the way, as well. So make sure to read those book examples and keep those ideas in mind in the corresponding exercises. Okay. cross product. This is another one where I've had to make some tough choices. And over the years, as I've taught this course and realized that as much as I have already kind of streamlined and, oh gosh, I can't talk about this, I can't talk about that, I've had to begrudgingly accept that there is a part of this section that I just can't talk about, and that is the proofs. There are some really elegant, instructive ideas in the proofs of the results in this section, and it makes me sad that I can't talk about those. So I am going to note as we go through this section where there are some proofs that I don't have time to present, but take a look. I mean, the checkpoints in the proofs that I'm going to not talk about are in the notes. And, again, good ideas in there, and I hope you'll take a look. Oh, I should also mention, every book takes a slightly different approach to presenting these ideas. Our book takes a very respectable approach. I have a preference for a different approach to present all these ideas. And the reason why there's all these options and all these different ways of doing it is because this is not a sort of linearly ordered fundamental idea followed by successive conclusions that build on top of each other. What we have is there's a bunch of ideas, and there's a sort of a nasty hairball of connections between all the different ideas, and you can zigzag your way through there in countless different orders, right? So if your goal is mathematical rigor, then you would do it a certain way, or various different ways that favor that point of view. If your goal is geometric intuition and satisfaction, then you take a very different approach. That's what I'm going to be trying to do here. I'm going to try to cut out as much opaque algebra as possible, and get to what I feel is the most intuitively satisfying approach through these ideas. So, okay, I'm going to start with an idea called the order of a list, and here is the big idea. If you have a list, now I emphasize let me do it like this. I'll just put a 1 there. One of the vectors is first. One of the vectors is second. So very importantly, the word list implies an order. Now I wrote here ordered list. That's what do you call it? A superfluous adjective. All lists are ordered. That's what a list is. I put the word ordered in here just for emphasis. So if you have a list, one of the vectors is first, one of the vectors is second. Okay, let's look at the geometric vectors themselves. Oh, whoops, trying to keep the colors straight. That's the first one. That's the second one. And notice that in the order that the list goes, green first, blue second, notice that the list is intrinsically counterclockwise. For those vectors A, B as drawn, A first, B second, counterclockwise. Does that make sense? Okay. Now, had the vectors been different, had the vectors been, there's A, still first, here's B, still second, notice that that order, A first, B second, is now clockwise. Right? So this idea of looking at the list that a couple of vectors are written in, the order that they're written in, this gives us a way to make a geometric interpretation of that order. Everybody on board? Okay. All right. Now, of course, not every list is one or the other of these. What if one of these is the zero vector? Then there is no clockwise, counterclockwise. Well, what if they point in exactly the same direction? What if they point in exactly opposite directions? There's various different scenarios in which neither of these would make sense. Conveniently, as it turns out, all of the leftover cases that don't fit neatly into one of these categories, they're all linearly dependent. So that's just handy. So these are the 3 scenarios for a list. That list is always 2 vectors in R2, either clockwise, counterclockwise, or dependent. Okay. All right. Now, who cares? Well, what does this do for us? A couple of neat properties to observe. These are mirror images of each other, right? If you have a counterclockwise list, such as that, notice that the reflections are clockwise. Well, that's just a little geometry, right? A little intuitive geometry. I think it's pretty satisfying. So, nevertheless, that's pretty natural. It's pretty geometrically simple. Right? Nice. Notice that if you trade the positions of the vectors in the list, if you put A where B was and B where A was, right, then that makes the list change order, right? So what had been a counterclockwise list, right, so this is counterclockwise, becomes a clockwise. Yeah. Okay. And then let's see here. The order of a list is independent of rotations. So, for example, if you have a let's see here, you have a list AB that is counterclockwise, like so. If you take the entire picture, you rotate the entire picture, right? This whole thing here, we're going to rotate everything around by some amount. Right? Everything gets rotated. Then notice that the resulting vectors still counterclockwise. So you might say rotating a picture preserves the order. Another way to say that, by the way, just for if we were to grab that clock off the wall, that clock, the second hand is going clockwise. If I were to show you that clock and you see the second hand going clockwise, if I were to rotate the clock, second hand's still going clockwise. Of course. All right, so again, geometrically very believable. Okay. There is a 3-dimensional version of this. It's not as familiar and relatable as the idea of clockwise, counterclockwise. Clockwise and counterclockwise are in everyday sort of like non-mathematical context. Everybody knows what clockwise and counterclockwise means. This 3-dimensional version of it is not as familiar, but it's just as meaningful. And here's how it works. So the first thing we're going to talk about is the idea of right-handed order. Again, it refers to a list. Again, the idea is that one of the vectors is listed first, one of the vectors is listed second, and one of the vectors is listed third. In order to make sense out of what right-handed means, you have to use your right hand. Very important that it be your right hand. Right? If you happen to be holding a pen in your right hand, you got to put it down. You can't just use your left hand instead. It's really importantly different. Right hand only. You put your index finger in the direction of that first vector. So you see I have my index finger pointing in the direction of A. By the way, you need to point your index finger parallel to your palm as you do so, right? So you can't, like, this, none of this. Right? So index finger parallel to your palm and has to stay parallel to your palm. Now, fine, let's see here. Now I have to take my second finger, my middle finger, and try to point my middle finger in the direction of the second vector, in this case, B. Now, you see, with my index finger like this, I can't make my middle finger point in the direction of B. My hand doesn't work that way. But keep in mind, I can rotate my hand. As long as my index finger stays parallel to my palm, I can rotate my hand around as needed, and now I can point my middle finger in the direction of B. That make sense? Okay, index finger parallel to the palm in the direction of the first vector, middle finger bent in the direction of the second vector. Again, by the way, the middle finger, of course, is not going to stay parallel to the palm. But the rule there is it has to bend the way fingers want to bend. No fair doing nonsense like this. That make sense? So only bending the comfortable direction. Notice now, the first two vectors define a plane. Notice that with your hand arranged as required, your thumb points on a pretty clearly identified side of that plane. You're going to be tempted to call it above in this case. Don't think of it as above. The vectors could be any which way, right? So above, below is arbitrary and it may or may not apply to the circumstance at hand. But your right thumb will point on one side of the plane. That third vector, C, if it points, as in this case, on the same side of the plane as your thumb, then that is a right-handed list. That make sense to everybody? Okay. Now, here is an example of a left-handed list. It's exactly what you think. Index finger parallel to the palm, parallel to the first vector. Middle finger, bending the way middle fingers want to bend, parallel to the second vector. Notice it's my left-hand thumb this time that points on the same side of the plane as the third vector. Okay. Notice also, if I were to try to convince myself that this actually left-handed order were right-handed, notice how it would crash and burn. Index finger in the direction of A. How do I get my middle finger to point in the direction of B without cheating? Well, I would have to do this. In which case now my thumb points down, but C is pointing up, and so again, not pointing on the same side of the plane. Everybody good? Okay. So we have right-handed, we have left-handed, and again, there are various cases that are neither, and it's a nice little geometric head-scratcher exercise to think through all the various versions of linearly dependent of three vectors in R3 and persuade yourself that, in fact, those various versions of dependence are exactly the cases that don't fit into one of these two categories. One of the vectors is 0, the other vector is 0, two of the vectors are 0, one of them is parallel to one of the others, one is a linear combination of the other two. It's various different versions, right? They all are exactly what's missing from those two categories. Okay. I claim this is a 3D version of clockwise, counterclockwise. Notice it's got all the same properties. Right hands are mirror images of left hands. Right? Easily noted. Trading two of the vectors in the list changes the order from the one to the other. Now, this is one you have to just kind of walk yourself through. I claim ABC is right-hand order for this list of vectors. A, B, C. Right? But if I switch the first two vectors and look at the list BAC, BAC is left-hand order. Yeah? Let's see here. Order is independent of rotations. This is another hand-waving proof. ABC is right-hand order. And if I were to rotate all of these vectors, this is still my right hand. Right? So, yeah, of course, right? Independent of rotation, just like clockwise, counterclockwise. And there's a fourth neat property that's worth mentioning, by the way, and that is that if you cycle, if you take the vector that is on one end of the list and take it over to the other end of the list, like so, this is called cycling. If you cycle the order of the vectors in a list, that preserves the order. And there's various different ways to think about this. Let's see if I can. Well, it's something. Okay, yeah, it's this right here. See what I'm doing with my hand here? Cycling amounts to this motion, and it's another good one to just take a moment and pull out your right hand and do this move, and notice that this is what's happening geometrically when you cycle the list. Okay, so I'm going to leave this there for just a moment. We're going to move on now and talk about some theorems you may have seen from linear algebra. If you haven't, so be it. But this is really important facts about determinant that we want to talk about here. Let's see here. It's going to take a minute to set up the theorem before we get to the result. Let's see here. Let me make this bigger. Okay, there we go. Okay, we're going to start with a list of vectors in R2. The first version of the theorem, the two-dimensional version of the theorem. Starting with a list, that means one of the vectors is first, one of the vectors is second. I'm going to take that list and I'm going to make a matrix. Got it. Color's wrong. I'm going to take the first vector and make that the first column. I'm going to take the second vector, make that the second column. So if you give me a list, I can generate a matrix. That doesn't mean anything. I'm just making stuff up. But if you give me a list, I can make a matrix by that process. A matrix, of course, defines a linear transformation. And now I'm going to make the clever observation that if you look at the unit square in the domain of that linear transformation, keeping in mind that the edge vectors of the unit square are E1 and E2, and if you ask, well, where does this edge vector go? Well, it's E1. Where does a linear transformation take E1? Well, it takes it to the first column. The first column being, of course, the first vector in the list by setup, right? And then likewise, the second edge vector of the square is E2. Where does the linear transformation take that? It takes it to the second column, aka the second vector in the list. Okay, how are we doing? I haven't made a statement yet. I'm just creating things. The statement will come momentarily. But you give me a list, I make a matrix, I make a linear transformation, I then make a parallelogram. Yeah? Everybody on board? So it turns out that these things that I've made from the list are all connected to each other in shocking ways. So here's the first shocking result. If you look at this matrix and compute the absolute value of its determinant, that will always give you the area of the parallelogram. That's incredible, right? How weird is that? Determinant, after all, is four-function arithmetic. Is this times that minus that times that. I mean, it's super easy to compute. It's entirely algebraic and super easy to compute with simple operations. By contrast, over here, the parallelogram, this is a geometric object, not an algebraic object. Area that we're talking about is a geometric trait of this thing. And how would you typically compute this area? Well, you'd have to drop a perpendicular. You'd have to compute this length, which involves square roots. You'd have to look at the sine or cosine of the angle. And so there's trig and square roots to compute an intrinsically geometric thing. This is just four-function arithmetic to compute an intrinsically algebraic thing. They do not seem like they should be related, but they are. Shocking, result. Is everybody on board? Curiosity, how many people saw this in math, linear algebra, whatever? Okay. Most. Okay, good. Yes.
I just want to ask, what's S in this case?
The unit square.
Oh.
Yeah.
So that would be then just like 1, 1?
Yeah, this point here is 1, 1, and this point down here is 0, 0. Yeah, and etc. Yeah. Okay, so that's the first result. Shocking. Here's the second result, and that is that the sign of the determinant, plus or minus, right, the sign of the determinant, tells you about the order of the list as to whether, A first, B second, is that counterclockwise or clockwise. So if you want to know, if you have a couple of vectors given to you, you want to know if it's clockwise or counterclockwise, you don't have to kind of draw the pictures and think about how they sit in space and use your imagination. You can just make a little matrix, take the determinant, see if it's plus or minus. Right? Powerful fact. Specifically, the relationship is that plus, minus, or 0 corresponds to counterclockwise, clockwise, or dependent, respectively. Okay. There is a third cool fact, which, by the way, this one that we just looked at, shocking, right? Really surprising. Third cool fact, and that is that there is a relationship between the determinant and the linear transformation, right? And specifically, the sign of the determinant tells you whether or not this linear transformation has a reflection, a flip, you might say, somehow involved in it. So again, determinant, very algebraic. Whether the linear transformation has a flipping upside down aspect to it is a very geometric idea, right? So again, really shocking that these would relate to each other. Now, what do I mean by a flip? What would it look like? It doesn't look like there's a flip how I have it drawn here. That is because as I have it drawn here, you'll notice that I had to draw a picture, and I put A there, and I put B there, and that is intrinsically counterclockwise, right? But what if I had instead, let's see here, so I'm going to change the deal on this picture. E1 going to the first column, let's suppose that was this vector. Right, and then E2, second column, the image is, let's suppose it was this vector. If this had been my picture, notice there's kind of unavoidably a flip that happened here. What would be the linear transformation that would happen on the plane that would turn this pair of vectors, green and blue, into this pair of vectors, green and blue? You can rotate all you want. You can magnify all you want. You can stretch, whatever, but the only way you're going to get counterclockwise to turn into clockwise is if you flip it over. Does that make sense? So I'm calling this down here, I'm calling this an inversion, if there's a reflection like that. I'm going to call it an inversion just to keep it a general term. But that's what I'm talking about. So again, in general, determinant does this for you. Positive, negative, 0 corresponds to whether there is not or is, or I'm going to say neither, and if there is, if counterclockwise turns into dependent, then in some sense there's kind of a smushing of the plane happening. And to say it in linear algebra language, then the column space is one-dimensional at most, right? So that's neither. The word flip just doesn't make any sense in that context. Okay. So those are the three cases. So really shocking facts about vectors in the plane. Here's the three-dimensional version. I'm going to be real quick with this because 1, 2, 3 vectors in a list, columns 1, 2, 3, matrix, linear transformation, and then of course you can make this thing that analogous to a parallelogram is called a parallelepiped. Right? So setup, analogous, right? The result, the theorem that I'm going to claim here, is, again, really analogous. The absolute value of the determinant tells you the volume of the parallelepiped. Again, algebraic to geometric. By the way, how would you compute this in a high school geometry setting? We don't even know. Right? They don't even do that in high school geometry, I don't think. You could brute force it, you could make it work, but this would be this would be hard calculation, right? Three-function arithmetic with determinant. Okay, so again, that connection, and then likewise, there's the connection as well to the linear transformation. Either does or does not have a flip in it. Oh, I circled the wrong thing. Sorry. The linear transformation either does or does not have a flip, corresponding with whether the list A, B, C is right hand, left hand, or neither. So, same results. Right? Here's the specifics. Positive determinant means right-hand order, means there is no reflection. Negative determinant means left-hand order, and there is a reflection embedded inside there somewhere. Right? Determinant 0 means that there's a squish, there's a dependence, everything's kind of gone haywire, and neither of the previous two cases makes any sense. All right, I'm not going to prove these results. The best way to prove these results, in my opinion, uses methods that are beyond what are appropriate to this course, and I could prove them using accessible methods, but it's just a bunch of hairy algebra that, frankly, I don't think is that instructive. And so I'm not going to do that proof at all. Okay, so two neat theorems, and by the way, notice how analogous these theorems are. This one is very, very analogous. This is the three-dimensional version of the previous. Okay, moving along. Let's talk about the cross product. Presumably you've seen the cross product before. So the formula, here it is. Neat observation to make is that this formula for cross product has three components, each of which is itself a little determinant. Which means that arguably the cross product itself is kind of sort of a 3x3 determinant. Is that a hand? No. Okay. All right. Yeah. Kind of a 3x3 determinant in the sense that, now this is a little bogus, it's a little nonsense, apologies. Technically, I'm not even sure if we should call this a matrix. Look at this. Some of the elements that are supposed to be real numbers, they aren't even real numbers. They're vectors. Is that you're just allowed to do that? That seems kind of bogus, doesn't it? I mean, a matrix is supposed to be made up of numbers. So this is a little bit garbage. I'm going to call this a symbolic matrix. And then when I say determinant, I mean ignore the fact that this isn't really technically quite a matrix, and just use the symbol, just follow just go across the top and use the minor cofactor formula and compute the determinant just symbolically only. And the amazing fact is you will get the cross product as this symbolic determinant. Is that cool? Okay. All right. Here's another cool fact. If you take this formula for cross product, and if you then dot it with some vector, C, just write it down. Just write down the dot product. As you punch up that expression, as you compute the green dot blue here, what you're going to find is you get exactly this determinant here. And that's just algebra. Right? But the process of computing this, let's see here, the process of cranking out that dot product is identical algebraically to a cofactor expansion along this top row. It just works out that way. Isn't that nice? So having made that observation, notice that we then have a new result that is not bogus. This isn't symbolic nonsense. This weird expression right here is a determinant. And in a very simple way, first vector, first row, second vector, second row, third vector, third row. This is not some weird symbolic memory trick. This is a deep statement about important operations that we've used in different contexts. Dot product, cross product, determinant. They're all related in this powerful way by this one formula. Right? So this is called a triple product. For whatever it's worth, I mean, technically, technically you want to be, you could argue that the triple product, meaning dot product with a cross product, needs a word because it is a new construction, and yet, what is it? Well, it's a determinant. So why aren't we just calling it determinant? Rhetorical question. The answer is technically determinant applies to a matrix, whereas triple product applies to a list of vectors. And now, yes, to be fair, if you have a list of vectors, it's really easy to turn it into a matrix. If you have a matrix, it's really easy to turn it into a list of vectors. Nevertheless, technically, they're different things, and so we have this new word. But when you see the word triple product in your mind, the very first knee-jerk reaction thing that you should think, when you see triple product, you should think, oh, determinant of the, the corresponding matrix, of course, right? But triple product is kind of pretty much just determinant. How are we doing? Is everybody on board? Okay. All right. Okay. What we're going to do with this is we're going to use the fact that we know some powerful results about determinant and some powerful results about dot product, and we're going to use this to learn about the cross product. I say we're going to. The proofs that I'm not going to have time to go through will use this formula to draw powerful conclusions about cross products. So that's just a little foreshadowing. Okay, so now begins the long list of cool theorem properties of cross product that, again, I don't have time to go through the proofs of. The first one, I'm fairly sure you all have seen this before. The cross product is always orthogonal to both A and B. You got to say orthogonal here. It's tempting to say perpendicular. You have to say orthogonal because A or B could be 0, and there's no such thing as perpendicular to 0. The cross product could be 0. No such thing as perpendicular to 0. So please interpret this as orthogonal in this context. Okay, now there's, again, great proof, and I hope you'll take a look. And you don't have to, and you're not responsible for it, right? But this proof right here is pretty neat, and I hope you'll give it a look-see. Okay, more neat facts. Whoa, what's going on here? There we go. When you cycle a list of vectors. Let's see, and I guess I can do one more. When you cycle a list of vectors like that, it doesn't change the value of the triple product. Now, if you take a sort of a non-determinate point of view on this, this looks mysterious, very shocking. That, for example, looking at this equation right here, you're telling me that somehow a dot product cross product expression where B is part of the cross product equals another such expression where B is not a part of the cross product. That looks. Wait a second. This isn't some simple thing like commutativity, right? Or associativity. This isn't a yawn, of course, kind of situation. This is a wait. What? How could that be? But it's true. And now again, you're not responsible for reading it, but ultimately the point here is that a triple product is a determinant. And so, I mean, from a certain point of view, you could think of this not as a statement about vectors and vector operations. You could view this as a statement about matrices. And determinants, right? Determinants of matrices, we already have a bunch of cool information about how, what happens to a determinant when you switch two of the rows and stuff like that, right? And so even though it looks mysterious in the vector interpretation, it's actually pretty believable. And I'm sorry, I just realized I'm out of time. So we will draw the line right here. We'll pick up here on Friday. Okay, see y'all later. Have a good one.